You write some code, you hit refresh, and poof, a web page just appears. But have you ever wondered what actually happens in that split second? Today, we're going to pull back the curtain on the hidden assembly line that turns raw code into the websites we use every single day. Seriously, it kind of feels like magic, right? You type out a bit of HTML and CSS, and somehow a fully formed interactive page shows up. But what is really going on in those milliseconds between your code editor and the pixels on your screen? Well, to get content on the screen as fast as humanly possible, browsers follow a very specific step-by-step process. It's called the critical rendering path. The best way to think about it is like a factory assembly line. Each station has a very specific job to do before it passes its work on to the next. And trust me, understanding this assembly line is the secret to building way faster websites. So here's the game plan. First, the browser parses the HTML to build something called the DOM tree. At the same time, it's parsing the CSS to create the CSSOM tree. Then, it combines those two into what's called a render tree. From there, it calculates all the geometry in the layout step, and finally, it paints the pixels to the screen. Let's walk through what each of these really means. Okay, everything, and I mean everything, starts with the HTML. This is ground zero. It's the first and most fundamental step, turning your markup into a structure that the browser can actually understand and work with. So once the browser starts chewing through that HTML, it spits out the document object model, or DOM for short. Now this is super important. The DOM isn't just a static copy of your text file. No, it's a live, in-memory tree of objects. Every single HTML tag you write becomes an object or a node, and they're all arranged in a family tree that perfectly mirrors your document structure. And this right here is a perfect, super simple example. On the left, you've got a tiny snippet of HTML. And on the right, that's what the browser sees. It's DOM representation. The body tag becomes the parent node, the H1 becomes its child, and yep, even the text welcome becomes its own little text node inside the H1. This tree structure is exactly what lets JavaScript find, change, add, or delete anything on the page. And here's the really clever part for performance. This whole process is incremental. The browser does not wait for the entire HTML file to download. The second the first few bytes arrive, it gets to work parsing and building out that DOM tree. This lets it start discovering other things it needs, like CSS and images, way earlier. All right, so while all of that DOM building is going on, the browser is actually multitasking. It's already starting a parallel task, figuring out how everything is supposed to look. And that, of course, brings us to the CSS side of the story. So just like it did for HTML, the browser builds a CSS object model, or CSSOM. You can think of this tree as a parallel universe to the DOM. But instead of holding content, this tree contains every single style rule for the page. That includes your code, any styles that get inherited, and even the browser's own default styles. But here is the massive, super critical difference you need to remember. Building the CSSOM is render blocking. What that means is the browser will refuse to render a single pixel on the screen until it has downloaded and parsed all of the CSS. So, why would it do that? It all comes down to the C in CSS, the cascade. A style rule you define at the very bottom of your style sheet can completely change a rule from the top. The browser can't risk showing the page with one style only to have it flicker and change a millisecond later. To avoid that ugly flash of unstyled content, it just plays it safe and waits for the entire CSSOM to be ready. Okay, so now we have two key pieces of the puzzle. We have the document structure, the what, in the DOM, and we have its style rules, the how it looks, in the CSSOM. The next logical step is to merge them together into a final blueprint for what's actually going to appear on the screen. And this combination is called the render tree. What the browser does is it walks through the DOM tree, and for each visible node, it finds the matching styles from the CSSOM and attaches them. Now, the key word there is visible. The render tree doesn't include everything from the DOM. It's a much leaner, filtered version that only contains what will actually be displayed. And this table just explains it perfectly. A normal visible element? Yep, it's in the DOM, and it makes it into the render tree. But what about an element with display none? It still exists in the DOM, but it gets completely left out of the render tree. It's like it was never there. It takes up zero space. Same for non-visual tags like head or script. But now look at visibility hidden. That one is included in the render tree. Why? Because it still takes up space in the layout. It's just invisible. All right, the blueprint is ready. With our render tree complete, the browser is finally ready for the last 2 stops on the assembly line, figuring out the geometry and then, at last, actually drawing the pixels. So first up is the layout stage, which you might also hear called reflow. This is where the browser basically plays Tetris. It calculates the exact geometry for every single item in the render tree, its precise size and position on the page, turning things like percentages into actual screen pixels. Once that geometric blueprint is set, the paint stage takes over, and the browser finally gets out its paintbrushes, converting those calculated boxes into the actual pixels you see on your screen. Okay, so at this point you might be thinking, this is really interesting, but how does this actually help me write better code? Well, understanding this whole pipeline is the difference between just guessing what's making your site slow and knowing exactly what's slow and why. And the awesome thing is, this whole assembly line isn't some hidden secret. You can actually see it in action, visualized right inside your browser's developer tools, specifically in the performance panel. Let's see how we can put this new knowledge to work. You know when a page just feels slow or janky? That's because one of the stages in this pipeline is causing a bottleneck. The performance profiler in DevTools shows you exactly where the browser is spending its time. Is it getting stuck trying to lay out the page? Or is it taking forever to paint? This knowledge turns you into a performance detective. When you run a performance trace, you get this thing called a flame chart. It might look a little intimidating at first, but it's actually pretty simple. All you have to do is look for wide bars. Those are the tasks that took a long time. And see how they're stacked? That shows you cause and effect. A JavaScript function up top might be the culprit causing a long purple layout event down below. So let's take a really practical example. Your page feels sluggish, so you record a performance profile, and you start hunting for a wide purple layout block. If you see one with a little red warning triangle on it, bingo, that's a huge clue. You can click on it, go to the Summary tab, and it will often show you the exact line of JavaScript that forced the browser to recalculate the entire page layout. A classic performance killer we call a forced reflow. So you see, the critical rendering path isn't just some abstract theory. It's a practical mental model for writing high-performance code. The next time you're about to write a line of CSS or JavaScript, you'll have this picture in your head of exactly how the browser is going to handle it. And that knowledge right there is the key to building websites that don't just work, but feel incredibly fast.